All right. Howdy, everyone. Welcome back. Hopefully, hopefully I had a nice break. I asked this question to my student class. I feel like to see who traveled the farthest. This is just an easy way to get a sense of what people did. Who traveled the farthest? It wasn't me. I didn't leave Florida. All right, throw it out there. Did anyone go far? Costa Rica. Okay. Anyone go farther than that? It's still in kind of the ballpark of Florida. Anyone travel farther than Costa Rica? Oh, you all lost compared to my first class. Someone traveled to Poland. So, yeah, anywho. My highlight was my daughter turned 3. So we had her birthday party, and it was very cute.
What was the theme?
There was no theme. Well, it's a good question, but if you asked her, she'd say there was cupcakes, and there was grapes, and there was presents, and her friends were there. Anyway, it was great. It was just at a playground. Yeah, we're not as good about doing a big old thematic one. It's great. They're fun when they are. But it was great. We had piñata. It was good. Yeah. So anywho, that was my highlight. I don't know if you've already started engaging with things again, but I know it takes a little bit to get the wheels spinning again. I know I felt it yesterday when I came back of just like, okay, getting back into the groove of things. So if you haven't already, hopefully today going through this review kind of reminds you of things. Obviously, our test is in 2 days. My hope, my optimistic expectation is this will go better than the first one. For a couple of reasons, but the biggest being I hope my thought process is you all are better at physics now than you were. You've spent more time. And the reality with physics is the skills that we use, you continue to use, like physics 2, you're going to use the same skills. Picture, givens, missing, getting used to working with equations, all that jazz, vectors, x and y components, all that stuff. So my hope is that you feel more comfortable and confident in those areas. Yes, it's new stuff, and yes, like, if you haven't practiced it, it's not going to go well. But yeah, we'll see. Fingers crossed. It is going to be 18 multiple choice. I kind of kept I wasn't sure whether to do more or less, but after kind of asking around, it seemed like 18 was decent from the last test. And so my thought process there is more questions means if you miss a question, your grade isn't affected as much. That's the benefit of more questions. And I've chatted through all that. So I did the test myself. It took me about 11 minutes to do all the multiple choice. Now, that is not like a kudos to me. Yay, I'm so good at this. I wrote the questions. Of course, I immediately know how to solve every problem. When I'm doing these and I'm kind of going through and timing myself, I am reading the entire problem, but I'm reading it maybe a little quicker probably than you would, because again, I've seen the problem before. I immediately know how to solve it because I wrote the problem and I've been doing physics for many, 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 many years. That's kind of a way of me determining how long it'll take you all. My hope my expectation is 60 minutes for the multiple choice, 20 minutes for the free response for you all. So hopefully me getting it done like 11. I don't know. We'll see if that translates. Hopefully it does. If it had taken me like 15 or 20 minutes, I would have like pared it down. So that's one of the ways I kind of determine these things. All right. I don't know if we'll get through everything in this PowerPoint. I have a lot of problems. I'll try to get through as many as I can. I'll definitely make sure to get through the slides where I have like the main ideas. But if I don't get through them all, I've already uploaded them completely worked out because I did it this morning. So the slides where these are completely worked out with all my handwriting is already done. And then if you want to hear/see me work through them, I also did that in the video from this morning's class as well. So if I don't get through everything, it's still available if you all want to go through it. These are all new problems in here that I made up this morning. And the problems that I'm going to show you all in here are kind of more the difficulty level of a free response problem. So these are kind of levels of a free response, but the individual skills in these could be multiple choice. So as we're going through these, the time it takes, it's more of a free response. Whatever. All right. Hopefully you know what's on the test at this point. It's conservation of energy and work, conservation of momentum, and I'll also talk on here. There's like a couple center of mass problems, and then fluids. Rule of thumb, it should hopefully be pretty easy to identify what type of problem it is. Fluids is like the most obvious. How do you know it's a fluids problem? There's fluids, like obvious. You're going to know it's a conservation of momentum problem if there's a collision or a separation. If things bump into each other / stick together, or they start together and separate. That's automatically going to be a conservation of momentum, like guaranteed. And then energy is, kind of what's left over, but energy is if something starts at some height with some velocity, ends at some height and some velocity, or if there's springs involved. These are fairly, my hope is that these are fairly easy to identify what type, and then that automatically kind of narrows it down on what you need to do. So, this slide has a bunch of things. It might be a little, so, we'll just chat through them, and as we go through each section, we'll kind of jump to a problem on it. So this first one is work. Work is F delta X cosine theta. Work is the amount of energy you gain or lose. That's the important idea. How much energy you gain or lose by some force. And what's really important here, one of the most common mistakes people make when it comes to force problems, is this angle. This angle isn't just the angle I give you in the problem. So I'm going to give you all a couple problems and you're going to see what I mean. This is the angle between the two variables in the equation. It's the angle between the force and the direction you're going. Delta X is how much you traveled. It's delta X is the direction you've gone. Did I go right, left, up, down, somewhere in between? Which way is my force? And that's how we're going to do this. So here's the first problem kind of on this. I pull a box with a force of 30 newtons at an angle of 20 degrees above the horizontal. If the box has a mass of 5 kilograms, how much work does gravity do if the box travels 3 meters to the right? So I'll give you all a few moments. Again, we got a lot of things here, so I don't have enough time to let you work through all of these in detail. But at least look at this, think about how you would solve this, and then I'll start going through it. And this PowerPoint is posted in the Files tab, so if you have a device or something like that, you don't need to rewrite the whole problem. You can just pull these up, delete all the ink in the presentation. You delete the ink by just hitting... Where are you at? Well, it's somewhere in here. There it is. If you go to the Review tab, there's a button that lets you delete everything. I had to put some ink first. All right, so there's my box. I pull it with a force of 30 newtons up to the right with an angle of 20 degrees. When we're solving these problems, remember the new strat, the more expert strat, is actually start with what we're solving for. Instead of doing the givens, we're actually going to jump right to what are we solving for. That's the way that people actually solve things in life, is you first need to identify what you're trying to figure out, and then you kind of collect your information. So we're solving for the work due to gravity. I'm not going to even necessarily write the givens yet. Again, kind of more the expert way of doing things is not actually looking at what's given, but thinking about how can I solve the work due to gravity. There's technically a couple ways, but there's one that's the most straightforward. The most straightforward one, if you want to find the work due to something, F delta X cosine theta, where FG is going to be my force. So that's just going to be M times G times however far I move times cosine of the angle. And this is where, if you haven't thought about this already, See if you can figure out what this angle is going to be. What is theta going to be? mg delta x, that's all really easy. And my pro tip to you, on your picture, draw the force. Draw the direction you're going. If you draw those two things, finding the angle is very easy. If you don't draw them, your brain has to work harder. So my force of gravity is down, and the direction I'm moving is to the right. This theta is not 20 degrees. This theta is not 20 degrees. Just because I gave you an angle in the problem doesn't mean it's the one you're going to use. This theta is the angle between my force and the direction of motion. That angle is 90. Long story short, the work done by gravity is 0. Cosine of 90 is 0. So the idea behind this problem, gravity's not adding any energy. If you slide something left and right, gravity did jack squat. Gravity didn't make it go faster. Gravity didn't make it go slower. Gravity didn't do anything. So the reason I give this problem, though, just because I give you an angle in the problem doesn't mean it's the angle you're going to plug in. So that's what this is for. All right, then I have another one just to stress this point, because again, this is such a classic thing that people make mistakes on. So I'm actually going to pull from one of the problems in the problem set. We're not going to solve the problem. We're just going to practice the skill of finding the angle. So it's this guy, the guy in the inclined plane. So it's, you got a person on a hill, and the person is going down the hill. If you were finding the work due to friction, what would you use for theta? If you were finding the work due to gravity, what would you use for the angle for theta? If you were finding the work due to tension, what would your theta be? So we're not actually solving this problem. We're just finding what would the theta be in the work equation. What would the value of theta be? And again, pro tip, draw the direction. I mean, the force is already on here, so that's kind of nice. Draw the direction you're going. Find the angle then between that and the force that you care about. If you don't draw it, it's much harder. Much more likely to make a mistake. All right. So the direction we're going is down the hill. If you think the answer to any of these is 60 degrees, you're wrong. None of these angles are 60 degrees. So if we're solving for the work due to friction, theta is going to be the angle between work and friction. We could just draw friction over here if you want. Boom, there it is. What's the angle between those? 180. Friction, the angle is always 180 degrees for when it comes to work. Friction's always directly opposite the direction of motion. That's like built into what friction is. All right, when we do gravity, again, we're going to kind of draw it here. Gravity is going downwards. So the angle I'm trying to find, I guess I could do it in a different color. Force of gravity is downwards. If I want this angle is not 60 degrees. And it's a little easier to see it if I kind of draw my delta x over here. If I draw my delta x here, we can see we make a beautiful triangle where force of gravity is down. This is the angle we're solving for. So here, the theta is going to be 30 degrees. And it's because if you make a beautiful triangle, if this is 60, then this is going to be 30. The angle between the force and the direction of motion for the gravity. Force is down, you're moving down the hill, it's 30 degrees. And then the last one is pretty straightforward. The work due to tension, it's the exact same. Tension is the exact same direction as friction, so that one's also going to be 180. Yeah.
So tension is always 180 as well?
Tension is not guaranteed to be 180. It's a good question. Tension is 180 because tension is up the hill and we're moving down the hill. But if instead the person was moving up the hill, then it would actually be 0. Yeah, it's a great question. So friction is the only one where it's always guaranteed to be a certain angle. Everything else depends upon the problem. So if they line up with each other, the angle is 0. If they're opposite each other, the angle is 180. If they're somewhere in between, we're somewhere in between. Yeah.
So since you have an angle, that's why the theta for gravity is 30 instead of 90 or...
Yeah, that one's 30 because gravity is straight down, but I'm moving not straight down, I'm moving down the hill, so the angle between force and gravity, the angle between the direction I'm moving and gravity in this case is 30. So, again, this is just more of a, when it comes to work, make sure you know how to get the angle. Don't just pick the one in the problem, because it might not be the one. It might be, it could be, but it's not guaranteed. All right, so great. That's the first thing, work. It makes things increase or lose energy. Work is positive, you gain energy. Work is negative, you lost energy. We then introduce conservation of energy, which says add up all our energies, and there's only 3 energies we've talked about. That's below this. We got gravitational potential, mgy. We have kinetic, 1/2 mv squared, and we have elastic potential, which is 1/2 kx squared. So you just go through your checklist. Now, before I guess we do that checklist, you need to choose where y equals 0. So remember, whenever you're solving a conservation of energy, if you want to say whether or not you have potential, you need to know where you're measuring. You need to say where y equals 0, and then if you're above that, y is positive. If you're below that, y is negative. If you're at that, y is 0. You get to decide. We'll do a problem on that just in a second. And then you got these energies. You just say, do I have them in the beginning? Do I have them at the end? Build the equation. And then work. There's work if there's any forces other than gravity or spring. If there's any forces other than gravity or spring, and they're making it go faster or slower, stuff like that, then we're going to have work done. So that's friction, air resistance, someone pulling it, anything that's not gravity or spring. It's most often friction, but it could be someone pulling it as well. And energy is a scalar. You don't work with x and y components. So we'll look at both of those. I have 2 different problems to kind of emphasize this. So let's do a simple thing. Energy is a scalar. You don't work with x and y components. Let's go ahead and try this one out. A 2-kilogram bird is traveling with a velocity of 3I minus 5j. What's the bird's kinetic energy? And there's the answer. So I'm just give you a few moments to think about how you would solve it, and then I'll start doing it. All right, so again, we're going to use a strat. What are we even solving for? Kinetic energy. Now, in this case, there is no beginning, there is no end. It's just, hey, it's moving. What is kinetic energy? So we're not going to use conservation of energy here. This is literally just what's the kinetic energy? What's the equation for kinetic energy? 1/2 mv squared. Now the question is, what do I use for v? Because I have 3I minus 5j. And you actually have a couple options here. One of the things you can do, so remember it's a scalar, so this v represents the total v. How do you get the total v? The magnitude of v, which is again another way of saying the total v, it's the square root of vx squared plus vy squared. You can They're vectors, x and y. How do you combine them? Pythagorean's theorem. So we can find that. Square root of 3 squared plus 5 squared. And that spits out some number, and that's my total velocity. When it comes to energy, we don't work in x and y. We work in just the total. It's much easier. That's why energy is so great. You don't have to split things into components. So we get a velocity of 5.38 meters per second. Great, super easy. Just plug it in now. What's my kinetic energy? It's going to be 1/2 times 2 times 5.83 squared. And you just plug all that in, and it's going to spit out roughly 34. Well, in this case, exactly, because I used the exact number. Great. Totally works. Now, one option that you can instead do, it's the same thing. If you didn't want to do the magnitude, something you could have done instead is the total kinetic energy. We generally don't want to work in components, but whatever you can if you want to. You can just find you can pretend like this bird was moving 3 in the x, and there's another object moving 5 in the y. This totally works. Like if you want to do this instead, go for it. It ends up getting you the exact same answer. And the reason for that is if you all pull out this m, vx squared plus vy squared, this is literally the exact same thing we just did. Vx squared plus vy squared is the total. A squared plus b squared equals c squared. It's the exact same thing. So, if you prefer to do it that way, it still spits out 34. Pick your poison. So if I give you something in components, either you can find like the energy, kinetic energy in the x and the kinetic energy in the y and add them together, or just find the total and do it that way. It's all the same. Great. So that's just getting the idea if it's a scalar. We don't care about direction really, but we can work in total. All right. A 500 kilogram car is traveling 20 meters per second and starts 5 meters above ground. The car later on is traveling 6 meters per second and is 2 meters above ground. Did the car gain or lose energy, and how much? And then I kind of give it away. I say the brakes cause this loss. Pretend like we don't know this next part. We'll get to this next part. Did the car gain or lose energy, and how much? So think this through, draw a picture, visualize it. What are we even solving for? All right, so you got a car, it's driving, it's some amount up, so it's moving 20 meters per second, and it's 5 meters up, and then at some point, somehow, some way, it ends up slightly down, and it's 2 meters, traveling 6 meters per second. Remember, whenever you draw this picture, you need to decide where y equals 0. So this is a conservation of energy problem. You need to decide where y equals 0. Like that's going to come into play. Now, to decide that, you have to realize it's conservation of energy. So I'm going to make the ground y equals 0. If you would prefer, you could actually make anywhere y equals 0. So for now, we're going to do this. So that's going to make my y final 2 meters. That's going to make my y initial 5 meters. If you instead wanted, you could have made it 0 when it's down here. And that would have made my y initial 3 meters and my y final 0 meters. And it just makes the math a little quicker. But that might not be intuitive for everyone. All right. What are we even solving for? How did I even know this is a conservation of energy? Well, I have a thing that's above ground and moving, and it ends up somewhere else and moving. That's like a flag. 2, what are we even solving for? What variable am I solving for? I'm solving for the energy gained or lost, and there's actually a symbol for the specific for energy gained or lost. This is work. Work is, by definition, the energy gained or lost. It's So if we just kind of write this out, sum of energy initial plus work equals sum of energy final. Work is literally energy final minus energy initial. It's your change in energy. It's how much you gained or lost, like you can see in the equation. So, this is just a classic conservation energy problem. What energy do I start with? What energy do I end with? Chuck it on in there, solve for W. So I start with potential because I start above. I'm not at zero. That's really how do you know you have potential energy? My Y isn't zero. I am moving to begin with, so I have kinetic. There are no springs, so none of that. And then at the end, I am still not at zero. It doesn't matter whether you're below zero or above zero, as long as you're not at zero. Obviously, if you're at zero, that turns to zero. Hopefully that's obvious. MV final squared. And you just chuck numbers in and solve. This is a classic. I hope at this point you're comfortable with conservation of energy problems. These are ones you have to know how to build it. You have to know how to build these equations. You're not going to find this. You're going to find this in the formula sheet. You're not going to find the thing below it because you got to build it for every single problem. So step 4 is just 500 times 9.8 times 5 plus 1/2 times 500 times 20 squared plus W equals 500 times 9.8 times. So I find the energy on the right side. It's 18,800 equals, what energy did I start with? So if you want to break this into pieces like this, you can. Equals 124,500 plus work, and you just subtract it over, and that's that. So work equals, subtract those two numbers, and you get that the work done is a negative 105,700 joules. It's negative. So did I gain or lose? I lost. I lost energy. If work is negative, I lost it. If work is positive, I gained it. It's exactly what you want it to be. The number on the right side of the equation was smaller than the number on the left side. It went down. Where'd it go? The environment, heat, energy. In this case, I say the brakes caused this. How much, and then I add a follow-up. How much power did the brakes dissipate if this happened over 3 seconds? Power, so this is something I'll remind you all of. There is literally only a single equation with power in it. If you see the word power, or you see the symbol watts, watts is the unit for power. Now you gotta be careful because one of the most common mistakes people make is they see in a problem 50W and they think this is work. It's not. It's a classic mistake that people make. Again, I know the test is timed and it's like you're trying to work through it quickly, so I'm trying to mention this. Do not make this mistake. If you see W after a number, it's not work. That's watts. And let me give you all an example that you're very comfortable with. If I say F equals MA, so here, let me just write both of these. Power equals work over time. Great, there's two different things. So F equals MA, and then 30M. This M is not mass. This M is meters. If I told you 30M, you're not going to think 30 mass. You're going to think 30 meters. Whereas F equals MA, you're not going to think F equals meters times acceleration, hopefully. M here is mass. The letter M is used for two different things. If it's in an equation, it's mass. If it's after a number, it's meters. W is the same way. If it's in an equation, it's work. If it's after a number, it's watts, and that's power. Just one of those, like, you've seen examples of this, just don't make this mistake. People make it all the time. Power is how much energy is used per second. It doesn't mean how much energy is destroyed. It doesn't mean how much energy is created. It means how much energy is converted from one form to the other. So in the case of the problem that we're going to do right here, this power here, how much power did the brakes dissipate? We know the car lost some energy. Where did the energy go? Heat. The brakes literally get hot. If you ever go down like a mountain road, you start at the top of the mountain, you get to the bottom, you do have to be careful with your brakes. If you're riding your brakes the whole time, they can get very, very hot. This is actually quite dangerous for semi-trucks because it's a lot of heat. They have to be careful not to ride their brakes the whole time. Energy doesn't get destroyed, it just gets converted. In the case of this, yes, this car lost energy. Where did it go? The brakes. The brakes got hot. So how much energy got converted to this heat every second? Really easy. Power equals work over time. If you see watts or power, you're going to use this equation. Really, really easy. Just chuck in the work in this problem, divide it by the time, and boom. We'll have how much energy is converted every second to heat. So I just need more room. So there's a few problems in the problem set with this. I don't remember if there's one on the practice test or not, but it's something important that you all need to know. Negative 35,233 watts. There you go. Every second, that much energy is converted from something to heat. And when you get to physics 2, you're going to see power again. Power is going to come up in physics 2 for the electrical circuits. It's how much electrical energy is also converted to like heat or light or things like that. You'll have a new equation for it, but it's the same idea. Yeah, and that's energy. That's kind of my representative sample for energy. Obviously, make sure you've done the problems. There's 2 problems. I think I mentioned them to you all. But let me just mention them now just in case I haven't. So there's 2 problems in the problem set you can skip in energy, and please, I say can, please do. They're not worth the time and energy. It's 12 and 13. I don't remember if I've updated them on here yet. It looks like I already deleted them. So that's good. I don't know if I deleted them on the ones I uploaded to you all though. Let's see. Yeah, I already deleted them from here because future semester I don't want them. It's the one with someone running, and it's like their joints. There's 2 problems involving someone's joints, where one is they're like running, and the other one is like they jump from 6 meters high. It's 12 and 13. If you see stuff about someone's joints, just skip it. They're not worth it. Otherwise, the rest are all reasonable to do. All right, energy. Done. Next topic is momentum. Momentum is really straightforward. Like I don't actually have too much to. There's like a couple problems I've came up with this. Momentum is always conserved, assuming no external forces. Rule of thumb: if there's a collision or a separation, use momentum. Like that's what you need to know. And then you need to know how to use momentum. But if there's a problem where things run into each other or they start together and they separate, you need to build conservation of momentum. You need to add up all the momentum you start with, and that needs to equal all the momentum you end with, and it's a vector. So if things aren't just moving left, right, or up, down, if they're doing a combination of up, down, left, right, then you need to do both. You got to do it twice. So you need to add up all your momentums in the y direction in the beginning and set them equal to all your momentums in the y direction at the end. If in the x direction, add up all your momentums in the x direction equals all your momentums in the y direction, or the x direction at the end. There's the Falcon problem. There's a billiard balls hitting each other. There's a lot of examples of this in the problem set. If you haven't gone through already. Momentum problems are super easy to make. And then we'll chat about this one at the bottom in just a bit. F equals delta P over T. But for now, let's go ahead and practice this. So person 1 has a mass of 50 kilograms and is running at 3I minus 2J ms. Person 2 has a mass of 75 kilograms and is running at 7I a third person arrives with a mass of 90 kilograms. If they all run into each other, get stuck together, what's the velocity vector for the third person such that everyone ends at rest? It's not a requirement that we end at rest. I specifically chose that for this problem just to make our life easier. They don't have to. Just because things run into each other doesn't mean they stop. That's an important thing to mention. I don't want to get in the bad habit like things always end at rest. No, not always. So yeah, think about this. Think about what's going on here, how you'd set it up, solve it, all that jazz. Then I'll start doing it. All right, so we draw a pretty picture. How many objects do I start with? In the beginning situation, how many things are there that are moving? 3 things. 3 people, 3 things. This is very important. If you don't realize there's 3 of them, then you're not going to be able to set up the equation right. So you got person 1 who's running 3 to the right and 2 down. There they go. You got person 2 who's running directly to the right. And then you got person 3. We don't know which way person 3 is going, so they are running some direction. We can guess very quickly after we get the final, but for now I'm going to not put it. They are moving. At the end, how many objects do I have? 1. They're all stuck together. One big blob. And are they moving? No. They're at rest in this problem. It's not a requirement, but in this problem, that is the case. Now, again, now we can predict, for them to stop, that person probably has to run against them to, cancel things out. So, great. We're going to now build, I'm not going to even write the givens. They're kind of in the thing. What are we solving for? We're solving for the velocity of person 3 in the beginning. How are we going to do it? Conservation momentum. M1 V1 initial plus M2 V2 initial plus M3 V3 initial equals M1 plus M2 plus M3 times V final. And next to all of these, I need to put little X's. Because this problem is not just left-right. This problem is not just up-down. They're doing both. So, I need to do this equation twice. So there's that one. I copy and paste it, and I replace all these x's with y's. If you only solve one of these equations, you will not get the right answer. They are both moving left, right, and up, down, and we have to do them separately. There is no shortcuts to this. There is no magic trick that makes it so you don't have to do X and Y. In the world we live in, when we're working with vectors, velocity, forces, things like that, you have to do X and Y separately. There is no way around it. Yeah?
Would this be like a free response question?
This would be a free response. Yeah, so all these problems that I'm basically doing with you all are basically all free response. How would I make this a multiple choice? Maybe I would ask the same problem, but I'd only ask you for the final velocity in the X, like the initial velocity in the X direction for them. So or the initial velocity in the Y. I'd give like a piece of this, if I made it a multiple choice. Yeah?
So, if I was reading this and we didn't have the 3i minus 2j for the velocity, then I would think only do it once for the X direction. So, do you only do X and Y because it has the meters per second like that?
So the reason we do X and Y is because person 1 is moving in the X and the Y. Yeah. If person 1 was only moving in the X and person 2 was only moving in the X, then we'd only have to work in the X. Person 3, by extension, would only be in the X. Because my Y would all be zeros equals 0. And yeah. So if any single object is moving in the X and Y, you have to do both. If any object is, or if one object is moving in the X, if instead this problem had been this person was running and I just put in the Y, then you'd have to do that. There's actually a problem on your all's practice test where I have a car that's moving east and a car that's moving south, and you have to break it into X and Y. Because one's moving left, right, one's moving up, down. You cannot just put those together. You got to do X and Y. So, the good news is my final velocity is 0 in both the X and the Y because it's at rest. So we're blessed that these terms drop out. So step 4, we just plug in numbers. So we have 50 times 3 plus 75 times 7 plus 90 times who knows what? Velocity initial 3x equals 0. You solve that. And then we do the same thing in the y direction. -2. You do have to put positives and negatives. These are vectors. Positive, negative matter. Momentum is the only thing on this test. Momentum and center of mass are the only things in this test that have vectors. Energy, you don't bother with the components, except for the one that... So I gave you all this example here that had components for energy. But we just combined it all together. We got the magnitude. We didn't bother with doing a separate X and what you could do that. But in general, we just work with the total. Momentum is the only thing on this test. You all got to make sure to do the problem twice in X and in Y. You do not do conservation of energy twice in the X and Y. It's not a vector. Energy you just do once, no matter what. All right, 75 times 0, because they're not moving in the Y, plus 90 times V initial 3Y. And then this is just a math problem that I'm not going to spend the time on. The answers are here. You could try it out, find those answers. If you solve this, you'll get that V initial 3x is negative 7.5. V initial 3y is 1.11. And that's my answers. So if you do the math, you'll find V initial 3x is negative 7.5. V initial 3y is 1.11. And that's the answers. And if I said, what's the total velocity of the person? I would then need to combine these, square root of that squared plus that squared. But yeah, this is a classic momentum problem. Now, something important here is I'm going to jump back to the other slide in just a second. This had 3 objects. Something I do not want you all to do is to just write down these 3 equations I wrote here and say, yep, I'll just use one of these. These only work for 2 objects. These equations here that I gave as examples do not work for 3 objects. So you need to be comfortable and able to build this. If I had 5 objects, there should be 5 of them. 6 objects, 6 of them. Do not get in the habit when it comes to momentum of just having these 3 equations I gave as examples and only using those. Because what if I give you 3 objects? Then what are you going to do? These are very if I have 2 objects, great, 2 objects, and then they bounce off each other and there's 2 objects. So how do you get good at doing this? You just do it, go through it. And it's literally just however many objects I should have that many momentums. If I have 3 objects in the beginning, 3 momentums in the beginning. 5 objects in the beginning, 5 objects in the beginning. All right, and then I've got another thing I want to test you all on, a skill that I want to make sure we haven't forgotten. Bob is running to the right with a velocity of 3 meters per second and down with a velocity of 2 meters per second. Jill is running with a velocity of 2 meters per second to the left. Just make the velocity vectors. I just want to see if you all make a common mistake here or not. There's no math involved in this. I'm not going to actually ask a question like this on the test, but you do need to have this skill because I'm going to ask questions that involve this skill. So there's just one thing I want you to be careful of. Bob's running to the right. Is that X component or Y component? X. Positive or negative? Positive. Great. He's also moving down. That's going to be the y component, positive or negative. If when you're doing a problem and I give you this and you don't realize that that 2 should be negative, you will get the wrong answer. If you're doing a momentum problem and I say something is moving down and you put that as a positive 2, you will get the wrong answer. So that's a skill that you all need to remember, that direction matters when it comes to velocity. And so Jill, in this case, she's moving 2 to the left, so that's negative 2 I hat. Just because the number's positive in the problem doesn't mean it's positive when you plug it in. And that's the thing to just be careful of. Up, down, left, right, all that kind of stuff. Be careful of. It matters. All right. Okay, now I'm going to jump over to this little thing here at the bottom real quick. F equals delta P over T. If I give you force and I give you time, this lets you find the change of momentum, which is great. This, honestly, is just F equals ma written differently. If we write this out, delta P is just mv final minus mv initial over time. If I factor out the m, v final minus v initial over t, if I divide that m to the other side, this equation is literally just F equals ma. F over m is A. A is Vf minus V naught over T. Like, this equation is not like a new equation. It just writes it in terms of P. F over m is A. Vf minus V naught over T. That's all literally the definition of acceleration. Change in velocity over time. A equals A. That's all this equation kind of comes from. But it's useful. I mean, it's I don't know. It's slightly convenient. But this next question I'm about to give you all, that we're going to use this, I'll straight up tell you we're going to use it. You could also, I could have given you this problem on test 1. It's not like a new skill per se. It's just looking at stuff with a slightly different paint job. 500 kilogram car is traveling 30 meters per second, runs into a wall. How does the force on a person compare if the time for the collision is 0.5 seconds compared to 2.5 seconds? Give you all some time to think about it. And then we'll do a center mass, and then I'll try to get through fluids. So we're trying to see how the force 2 compares to force 1. Is it 3 times bigger, 2 times bigger, 1/3, 1/5, 1/7? Is it bigger, smaller, and by how much? That's what the question's asking. Just looking at this problem, you might have an intuitive idea. Whatever the answer is should match your understanding of reality. This is something you very likely could have gotten right, even if I had taught you no physics. As weird as that sounds. If you had to guess the right answer, you'd have a pretty decent chance as long as you were thinking about it carefully. So, how do we actually solve this, though? Maybe a bit more rigorous. So, I'm going to write the equation. F equals change in P over T. That's the one we're going to use. Why are we going to use that? Let's write this maybe slightly differently. F equals mv final minus mv initial over t. I know m, I know v final, I know v initial, I know the time. You could straight up just find the forces and compare them. Totally works, brute force it, great. There is a little bit of a shortcut though. If you realize that the time 2 is 5 times time 1. 2.5 is 5 times bigger. So it's a little bit, this is kind of a ratio problem. If this changes, how does this change? Anytime you have a problem like that, if this changes, how does this change? How do these two things compare? It's useful to figure out what numbers changed in the ratio of those. So again, you can brute force this, compare them, great, works perfectly fine. I'm going to do it the quicker way, which is the ratio way. So F1 equals mv final minus mv initial over T1. F2 equals mv final minus mv initial over T2. My final and my initial velocity are the same in both. They both start at 30 meters per second. They both end at 0. What's the only thing that changes? The time. So I'm going to take this force 2 and I'm going to swap this in. I'm going to swap this time into here. So I get mv final minus mv initial over 5 times t1. I pull out the number that changed. I pull out that 5. It's on the bottom though. And I have mv final minus mv initial over t1. This whole thing here is force 1. So long story short, my force 2 is 1/5 my force 1. That's the final result. And then if we just think through, does this make sense? Does this make sense? If I run into a wall or I run into a pillow, which one happens quicker? Wall or which one slows me down quicker? Wall or pillow? Wall. Great. Which one's a bigger force? Wall. Shorter time, bigger force. Longer time, smaller force. According to this, whatever my force is for the first one, my second force is 5 times smaller. Make up numbers for this. If my first force was 10, 10 divided by 5 is 2. One of the things that throws people off when we write these ratios is which one's bigger. Just make up numbers. So is F2 bigger or is F1 bigger? Make up a number. If F1 is 10, so if I just make up a number and F1 was 10, then F2 is going to be 2. 2 is smaller than 10. You can always do that if you want to check your ratios and see if they make sense. Is it bigger or smaller? And this makes sense. My bigger time, smaller force. That's what this says. So there's a bunch of these ratio problems sprinkled into all the practice I give you, quizzes, practice test I gave you, top hat questions. If this changes, how does this change? Like, that's an important skill. And a lot of these, if you have a conceptual understanding, you often don't even have to do the math, but math's helpful. All right. Last thing I need to tell you all about momentum is you have 2 different types of collisions, elastic versus inelastic. What I need you all to know is elastic, they bounce off each other. Energy and momentum are conserved. Both are conserved. The amount of energy I start with equals the energy I end with. The amount of momentum I start with is the momentum I end with. Inelastic, that's where they stick together, or if something separates, only momentum is conserved. And this is pretty easy to show why only momentum is conserved. I got some blob and it's not moving. What's its kinetic energy? If it's not moving, what's its kinetic energy? 0. Great. My blob then explodes into 2 parts. And they're both moving. What's my kinetic energy now? Not 0. Because kinetic energy, if you all remember, is 1/2 mv squared. Kinetic energy is always positive. It is impossible to have a negative kinetic energy. So if something explodes into 2 parts, it started with 0 and it ended with not 0. 0 does not equal not 0. Did I prove that energy is not conserved? I just need you all to know these statements, though. I need you all to know these ideas. If you're afraid of forgetting them, write them down. All right. One last thing in this is I got to teach you all about center of mass, and then we'll get to fluids. Center of mass is really straightforward. It's vectors, x and y. There's an x center of mass. There's a y center of mass. You got to do them separately because it's position and position. If you all remember kinematics, you had to do x and y separate. And it's just m times the x position. Add that up for every object. If you have 5 objects, add them all up. And then divide it by all the mass. And then you do that for the y. M times the y position of each object. Add them all up. Divide it by the mass. And I'm going to do a quick example of this. Just to show you all. Object A is 3 meters above the origin. So there it is. 3 meters above the origin and has a mass of 7 kilograms. Object B is 2 meters to the left of the origin. There it is. It's got a mass of 15 kilograms. The problem says, what is the distance from the origin to the center of mass? We're not solving for the x center of mass. We're not solving for the y center of mass. We're solving for the total distance. Where is the center of mass relative to the origin? So how are we going to do that? We're going to get the x center of mass squared, y center of mass squared. Total distance is combine the x and y. If you want to find the total of x and y, triangle. So, x center mass is going to equal x1 times m1 plus x2 times m2. Here, I'll write this out both ways. It's x times n over sum of m. So I get my x position of object 1 times the mass of object 1. X position of object 2, mass of object 2. If I had 7 objects, keep doing it. x3, m3, x4, m4, yada, 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 yada. And then you just add up all the masses. However many there are, add them on up, easy peasy. Y center mass, do the same thing, but just replace it with y's instead of x's. Y position of object 1, mass of object 1. Y position of object 2, mass of object 2. And I'm just going to do a little coordinate axis here. Object 1 is located at 0, 3. Object 2 is located at negative 2, 0. So object 1's x position is 0 times 7 plus negative 2 times 15. Divided by 7 plus 15. And then my y center mass is going to be 3 times 7 plus 0 times 15, all divided by 7 plus 15. So that gives me my x center mass, that gives me my y center mass. Neither of those are the answer. I didn't ask where it's located horizontally. I didn't ask where it's located vertically. I asked for the distance from the origin, the total, everything together. So we got to bring them together. So the first one's going to be 1.36, negative 1.36. So my x center mass is left of the origin. Makes sense based on the picture. And the other one is going to be 0.95. So then if I want my r, I just chuck those in. 1.36 squared plus 0.95 squared, and that will spit out the 1.664 meters. So there's an example of center mass problem in the problem set. I think there's 1 or 2 in the practice exam. There's going to be 2 of them on the exam. Make sure you know how to do them. 1 conceptual, 1 math. All right. In my last bit of time, 20 minutes, we'll get through fluids. It may or may not be able to solve all the problems, we'll see. There is one problem in the problem set for fluids that I don't want you to do because it's not the problem I wanted it to be. If y'all go to fluids, and you go the second to last problem, did I already delete that one as well? Yeah, I deleted it. The second to last problem says something about like a PINOT, P-I-N-O-T, or something like that. Skip it. If y'all see a problem, it's the second to last one. Not this blood one. Not this blood one. It's something about a Pinot tube and things like that. That one you can skip. I thought it was a Bernoulli's problem. It's not. It kind of sort of it is, but... Alright. But let's go ahead and get into fluids. Alright, fluids is a bunch of simple concepts, but there's a bunch of them. And there's some more complex, like involved problems. That's the 3 I picked. So the 3 example problems I picked don't represent everything, just because I don't have time. However, the practice exam I gave you all, that has all the different ideas, and of course the problem set does as well. Also, remember you all have a fluids quiz due this Saturday. Remember the purpose of these quizzes. The purpose of these, you get 4 attempts, it's to check if you understand the idea. Do not wait until after our exam to do the fluids quiz. because the purpose of the quiz is to see if you understand it. I would much rather you realize there's things you don't understand before the exam versus showing up and realizing, oh crap, I don't understand fluids on the exam. Please try the fluids quiz before the exam. It's practice. It's a check for you. That's the only reason that assignment exists, is for checks for you all on a weekly basis to see if it makes sense. If you don't do the fluids quiz, you're just kind of making your own, like, you'll find out whether you know it on the test, I guess. And that's not the ideal. They're good problems. Like, I wrote all the problems for it. I think they're good. All right. Density equals mass over volume. I really hope you're familiar with this. If not, it's super, super important. It comes up in a lot of problems. Density is super important when it comes to fluids. We don't really actually work with mass. There's only one equation that has mass in it, and even to get this mass, it's down here at the bottom, you have to use density. Like every problem we give you with that, you still have to use it. So density is mass over volume. Definition. Great. Easy peasy. I'm going to straight up tell you, I'm not going to give you a problem where I say the mass is this, the volume is this, what's the density? But you will have problems where you're going to use this equation. And you'll see what I mean. The 3 examples I'm going to give you, I think one or both of them are going to need it. All right, pressure equals force over area. That's just a definition of pressure. Yeah.
You have to convert, like how you said, like if it's like square inch, you have to do it twice.
It is, yeah, if I give you centimeters squared, yeah, you do need to know to convert to meter. Always get to meters. Always get to meters. If I give you liters, convert to meters. If I give you centimeters, convert to meters. If you have centimeters squared, yeah, I'll jot that down up here. So remember, 1 centimeter squared is not 0.01 meters squared. That is not the right answer. 1 centimeter is 0.001. You've got to do it twice. If you go through the practice, there's a lot of chances to practice that, the problem sets and all that. It's an important thing to realize. If this is squared, you got to do it twice. If it was cubed, you'd have to do it 3 times. All right, great question. Pressure equals force over area. Again, I'm not going to probably give you something as boring as, hey, the pressure is this, the area is this, what's the force? What I might give a problem on, and you'll see this in practice test, is when it comes to hydraulics, the way we use pressure in a fluid, any increase in pressure somewhere results in the same pressure somewhere else. P1 equals P2. Well, if pressure is force over area, then the other pressure is force over area. And so there's a lot of problems I gave on this where I make the area 4 times bigger. What happens to the force? I make the area 1/2. What happens to the force? There's a problem like this in the practice test. Make sure y'all tried those out. Very important idea. It's how your brakes work. It's how construction equipment works. It's so useful. All right. Yeah, and again, I don't think I have an example on that one. Nope, not yet. All right. Let me see which ones I do have. Okay. Next one is pressure equals rho GH. The farther, or rho HG, doesn't really matter. The deeper you get, the higher the pressure. And this does not depend on the width of the container. The pressure at the bottom of a 10-meter straw is the exact same pressure 10 meters down in the ocean. Doesn't matter how wide your container is. Even if it's as big as the ocean, pressure only depends, when you're moving up, down, it only depends upon the height, assuming the fluid's not moving. If the fluid's moving, we'll see that problem in a second. But if your fluid's not moving, your pressure is given by this equation. Rho Hg. Really straightforward. There's examples of that. We're going to see this equation in a bit in another problem. All right, the last one on this slide, and this is the first one we're going to do a practice one on. The buoyant force. If you put an object in a liquid, the liquid pushes up on the object, no matter what. This is called the buoyant force. Just because something sinks doesn't mean that the fluid's not pushing up on it. It just means it's not pushing up on it enough to float. But it's still pushing up on this. You all know this. If you go in water, you feel more weightless, even if you sink. If you put something really heavy in water, it feels like less weight. Why? There's this buoyant force pushing up. That's basically making it seem like it weighs less. How much is this buoyant force? Really, really simple. It's the mass of the fluid that the object takes up, however much that object takes up. If you imagine that object was water instead, however much that mass would be, multiply that by g, and that's the buoyant force. So, let's go ahead and do a problem on that one. I'm going to switch the location of it. A chunk of lead with a mass of 7 kilograms is placed in water. What's the buoyant force on the lead? Yeah.
Since in this case, gravity is actually like pushing up, is it always going to be positive?
So the buoyant force is always going to be positive, yeah. So gravity's still down, but the buoyant force is up. Yeah, so this M fluid times G is the buoyant force, and it's actually, yeah, it's up. It's how much the water pushes up on it. The lead's getting pulled down, the buoyant force is pushing it up. In the case of this problem, lead sinks because it's gravity wins, but. Alright, so, what are we solving for? The buoyant force. Like, boom, we know we're solving for buoyant force. That's literally the only equation with buoyant force. Alright. The next step is hopefully obvious. You might not know how to get it, but like what we need to find next is hopefully obvious. The buoyant force equals the mass of the fluid times G. What do you think we have to find? We got to find the mass of the fluid. Like, that's the only way to solve it. All right, so now this is the part where how do I find the mass of the fluid? So to find the mass of the fluid, now I gave you density in this problem. That's kind of a hint. So this is where density is going to come into play. There's literally only one equation in fluids that has mass in it. Okay, I guess there's this one. There's only one other equation with mass in it in the fluid stuff. Density is mass over volume. It's literally the only equation in the fluid section that has M in it. So like that's the one we're going to have to use. Okay, so this is density of fluid equals mass of fluid over the volume. Rearrange this. Mass of fluid equals density of fluid times the volume. What's the volume? The volume is how much space is taken up, how much space is taken up by this object. The volume here is the volume of the lead. If you put an object in water, however much space it takes up is how much water it takes up. They're the exact same. If you put this marker in water, the amount of volume of water displaced is the volume of the marker. You all know this when you've like played with a graduated cylinder and you want to figure out the volume of the object. You put it in the water, you saw how much the water went up. The volume of the water is the volume of the fluid. Like the volume taken up is the same. Great. I know the density of the fluid. How do I find the volume of the fluid? Well, there is literally, I think, only one equation with volume in. I think there's only one. It's the same exact one. But now we're not going to use the density of the fluid. Density of lead equals mass. If we can find the volume of the lead, we can find if we can find the volume of the lead, we know the volume of the fluid. If we can find the volume of the fluid, we can find the mass of the fluid. If we can find the mass of the fluid, it's just a bunch of density. So, volume equals mass of lead divided by density of lead. How much space does the lead take up? That's how much water is taken up. That'll give us how much mass of the fluid, and you go from there. Again, there's a lot of examples. There's a couple examples of this in the problem sets. So now we just do it. Let's find the volume. That's going to be the mass of the lead. 7 divided by 11,340. It's not going to take up very much space. 7 divided by 11,340. That comes out to 0.000617 meters cubed. It's not that big. Great. That means the mass of my fluid, here I'll do it in a different color. The mass of the fluid is going to equal the density of the fluid, that's 1,000, times the volume taken up, which is going to be 0.617. And then finally at the very end, if you all want the buoyant force, it's just going to be that mass times G. And that spits out 6.05. So, there you go. That's how much the water pushes up on it. It seems like a bunch of steps, but each individual equation, it's just density equals mass over volume, density equals mass over volume, density equals mass over volume. And that's how much the water pushes up on it. And again, there's a few examples of this. Make sure you try to go through them. Buoyant force is pretty important. It explains why everything water experiences this. And this equation was discovered in 400 BC. Like, it's from a long time ago. So, it's pretty core to fluids. It's a nice, straightforward equation. You just got to do some density stuff. All right. Okay, a couple more ideas. Literally 2. Yeah.
On the slide up,
This one?
is this supposed to have 2 zeros or 3?
Did I miss a 0? Let's see. You're right. I did miss a 0. Thank you. Another thing I want to remind you all of, this is on the formula sheet. If I give you liters, you need to convert to meters cubed. This is on the formula sheet. Like, you don't need to have this memorized. Please do not make the mistake. If I give you liters, you need to convert to meters cubed. 1 liter is not 1 meter cubed. This is very obvious if you spend 5 seconds thinking about it. If you go to the store and you buy a liter of soda, a 2-liter bottle is like the classic. That 2-liter bottle does not take up a meter by a meter by a meter. If you say 1 liter equals 1 meter cubed, you are saying a 1-liter bottle takes up a space that's a meter by a meter by a meter. If you just think about that, that doesn't make sense. So that's this again. This is on the formula sheet, but it's just something to be careful of. It's a trap that people fall into. All right, couple more things, and then we're good. And these are the last 2 problems I'll try to get through. Flow rate is exactly what it sounds like. It's the rate of flow. It's how much fluid passes through a pipe in a certain amount of time. It's either liters per second or meters cubed per second. Again, that reminder, 1 liter is 0.001 meter cubed. So this flow rate is volume over time. It's also your cross-sectional area times velocity. This is in the formula sheet. I literally copied and pasted this. Why is this flow rate important? It's a constant. The amount of water flowing through a pipe is a constant. At some places it might move slower, at some places it might move faster, but the amount going through it overall is a constant. Q1 equals Q2, which means A1V1 equals A2V2. As the area gets smaller, the velocity gets bigger to compensate. You put your thumb over the end of a hose, water goes faster, so that flow rate is a constant. Area 1 times velocity 1 equals area 2 times velocity 2. So I'm going to quickly solve a problem on that, and then I'll do Bernoulli's really quick as well. 2 pipes each have a radius of 2 centimeters. Fluid in them is traveling at... This problem is almost identical to one of the quiz for this week. 2 pipes each have a radius of 2 centimeters. Fluid in them is traveling at 9 meters per second. The pipes combine into 1 pipe. If the velocity in the big pipe is 7 meters per second, what's the radius of that pipe? Area changes. Radius changes means area changes. And therefore, my velocity changes. So, this one we are solving for the radius in the big pipe. Radius is not area. Radius is not area. That's another, people in a rush tend to make that mistake. So we're going to use flow rate. Things get faster as the pipe gets smaller. A1V1 equals A2V2. Every single problem I'm going to give you, it's always circular cross-sectional areas. Every pipe is going to be a cylinder. I'm not going to give you any square pipes because they don't, like, no one makes square pipes. Your blood vessels, cylinders. Pipes, cylinders. Everything that water travels through is cylinders. They're better. They're generally stronger. I'm not going to get into too much why. Square pipes wouldn't be as strong. Now, the area of a cylinder, the area of a circle, is the one we're going to use. It's going to be pi r1 squared. So this is my left side, but I am missing something. And I want you all to look at this and see if you can figure. Before I do the right side, I want to see y'all. So this is the area of a circular pipe, pi r squared, times the velocity in those pipes. I want to see if y'all, there's something I'm missing. I want to see if y'all can spot it. Spend 10, 20 seconds looking at it. How many pipes did I start off with? So I don't just have the area of one pipe, I have the area of both of them together. You can't just pretend it's one pipe because it's not. It's two pipes. So there's two of them. Whereas on this side, there's just one pipe. And you just chuck in the numbers and you solve. So if you want to know the radius 2, we're just going to plug in numbers. So 2, the pi's cancel. That's kind of nice. 2 times, and I'm going to go ahead and convert my centimeters, times 9 equals radius 2 squared times 7. If you do the math, you'll find that R2 is 0.032 meters, which is the exact same thing as 3.2 centimeters. And there you go. Again, you're like, man, I'm not sure about fluid. Just go through the practice problems. Go through the problems, do the quiz. Like everything in this class, the only way you're able to do these problems is if you practice them. There is no shortcuts. Practice test has a third of the multiple choice in this exam is fluids, so it is important. The free response will only be energy and momentum. The free response will only be energy and momentum, but a third of the multiple choice is fluids. All right. Last thing I need to teach you all, and the good news with this last one is it should hopefully look similar to something you've seen before. It's Bernoulli's principle, i.e. it's basically conservation of energy but for fluids. Everywhere instead of mass, you put density. You got 1/2 density velocity squared plus density gy. Like, hopefully this looks like energy to you. Hopefully you've done enough energy problems that you're like, wow, that looks like kinetic energy. That looks like gravitational energy. And then you just got these pressures at the beginning pressure and final pressure. So what would a problem look, and important concept, higher velocity has lower pressure. It's not intuitive whatsoever, but according to this, according to the physics, according to reality, that is what happens. I haven't figured out how to teach it intuitively. So real quick, I'm just going to show you all this problem. I'll set it up. We're not going to have time to completely solve it, but I'll post, it's already posted, fully worked out. Water is some pipe traveling 3 meters per second at a height of 5 meters. Later on, it's velocity of 9 meters per second at some height. If that pressure increased by 600 Pascal, that's the metric unit for pressure, what height did I end with? It's energy, but with fluids. Velocity, height. Velocity, height. So I got P initial plus 1/2 rho V initial squared plus rho GY initial equals pressure final plus 1/2 rho V final squared plus rho GY final. We are solving for Y final. And so when you plug in the numbers, and this 600 Pascal, I'll just do it over here. PF minus P naught equals 600. So then you just quickly, I'll chuck in the numbers here just so you can see it all. So 1/2 times 1,000 times 3 squared plus 1,000 times 9.8 times 5 equals PF minus P naught is 600. So if you kick that over, boom, there's a 600. Times 9 squared plus 1,000 times 9.8 times Y final. Solve for Y final. It looks worse than it is. If I gave you all a problem like this in a test, I would probably just make the height the same at the beginning and the end, or make the velocity the same at the beginning and the end, and you would do it. And that wouldn't be too bad. All right, and that's it. We did it. We got through it all. Please practice some, y'all. There's no substitute for it. I'll see you all Thursday. It's going to be great.
So did you just not put a no pressure because all of a sudden was 600 more?
Yeah. Yeah. No, that's a good, yeah.